Welcome back to another exciting episode of Decentralized Application Development Crashcasts. I'm your host, Sheila, and I'm here with my brilliant co-host, Victor. Before we dive in, I want to remind our amazing listeners that if you're enjoying our content, please take a moment to rate our podcast on your preferred platform. Your support means the world to us.
Absolutely, Sheila. Your feedback helps us improve and reach more developers interested in decentralized technologies. Now let's get into today's topic, shall we?
Definitely. We're continuing our journey through Season 2, focusing on core hole-punch technologies. We're in Chapter 2, exploring Hyperswarm networking, and today we'll be discussing a crucial aspect, handling disconnections. But before we start, I have a brain teaser for our listeners. Here's the question. In a P2P network, why is handling disconnections often more critical than in traditional client-server architectures?
Ooh, that's a great question, Sheila. It really gets to the heart of P2P network dynamics. I'm sure our listeners will have some interesting thoughts on this. While they ponder, let's break it down a bit. In P2P networks, we're dealing with a distributed system where each peer can be both a client and a server. This unique structure creates some interesting challenges when it comes to maintaining connections. What do you think, Sheila?
Well, Victor, I imagine it has something to do with the decentralized nature of P2P networks. In a client-server model, if a client disconnects, it usually only affects that specific client. But in a P2P network, each peer plays a more integral role in the overall system. Am I on the right track?
You're absolutely right, Sheila. That's a great starting point for our discussion. Now let's dive into the concept of handling disconnections in P2P networks, specifically in the context of Hyperswarm. First, can you give us a quick recap of what we covered in our last episode about establishing connections?
Certainly. In our previous episode, we discussed how Hyperswarm establishes connections between peers using its distributed hash table, DHT, for peer discovery and topic-based networking. We learned about the process of finding and connecting to peers interested in the same topics. Now we're moving on to what happens when those connections are lost.
Excellent summary, Sheila. Now let's talk about why handling disconnections is so crucial in P2P networks. In a decentralized system like Hyperswarm, every peer contributes to the network's functionality. When a peer disconnects, it can affect data availability, routing efficiency, and overall network stability. That's why having robust mechanisms for handling disconnections is essential.
I see. So, Victor, what are the different types of disconnections we need to consider?
Great question. We generally categorize disconnections into two types: graceful and abrupt. Graceful disconnections occur when a peer intentionally leaves the network and can inform other peers. Abrupt disconnections happen suddenly, often due to network issues or crashes. Hyperswarm needs to handle both types effectively.
That makes sense. How does Hyperswarm detect these disconnections?
Hyperswarm uses a combination of techniques to detect disconnections. One primary method is through keep-alive messages. These are small, periodic messages sent between connected peers. If a peer doesn't receive a keep-alive message within a certain time frame, it assumes the connection might be lost. Additionally, Hyperswarm leverages the underlying TCP connection status to detect abrupt disconnections.
Interesting. It's like checking if someone is still on the other end of a phone call by saying, "Are you there?" every now and then. Now, once a disconnection is detected, what strategies does Hyperswarm use to handle it?
That's a great analogy, Sheila. When it comes to handling disconnections, Hyperswarm employs several strategies. First, it immediately updates its internal state to mark the peer as disconnected. This prevents the application from trying to send data to an unreachable peer. Then, depending on the application's needs, it might attempt to re-establish the connection.
I imagine reconnection attempts could be tricky. How does Hyperswarm manage that?
You're right, reconnection can be complex. Hyperswarm uses a backoff algorithm for reconnection attempts. This means it starts with quick retry attempts, but if they fail, it gradually increases the time between attempts. This approach prevents overwhelming the network with reconnection requests while still trying to restore the connection.
That's clever. It reminds me of how we might call someone back immediately if a call drops, but wait longer between attempts if they don't answer. Victor, can you tell us about how Hyperswarm manages state during disconnections?
Absolutely, Sheila. State management during disconnections is crucial. Hyperswarm maintains a bit field of the data it has received from each peer. When a peer disconnects and later reconnects, this bit field helps in efficiently resynchronizing data. It allows peers to pick up where they left off instead of starting from scratch.
That's fascinating. Now, I'm curious about how all of this impacts the application logic and user experience. Can you elaborate on that?
Certainly, the way Hyperswarm handles disconnections significantly affects how developers design their applications. For instance, applications need to be resilient to sudden peer disconnections. They should gracefully handle scenarios where data might be temporarily unavailable due to peer dropouts. From a user experience perspective, applications might implement features like offline mode or local caching to ensure smooth operation even when connections are unstable.
This is all really enlightening, Victor. Before we wrap up, could you share some common pitfalls or best practices when it comes to handling disconnections in Hyperswarm?
Of course, one common pitfall is assuming connections will always be stable. It's crucial to design your application with the expectation that disconnections will occur. A best practice is to implement proper error handling and logging for disconnection events. This helps in debugging and improving your application's resilience. Also, it's important to communicate connection status to users transparently, so they understand what's happening behind the scenes.
Thank you, Victor. This has been incredibly informative. Now, let's reveal the answer to our quiz question. The reason handling disconnections is often more critical in P2P networks than in client-server architectures is that in P2P networks, each peer plays a crucial role in maintaining network functionality, data availability, and routing. When a peer disconnects, it can have a ripple effect on the entire network, potentially affecting multiple peers and overall system performance.
Excellent explanation, Sheila. To summarize today's episode, we've learned about the importance of handling disconnections in Hyperswarm, the types of disconnections, detection mechanisms, strategies for handling them, reconnection attempts with backoff algorithms, state management during disconnections, and the impact on application design and user experience. Remember, in P2P networks like Hyperswarm, expecting and gracefully handling disconnections is key to building robust, decentralized applications.
Thank you, Victor, for these invaluable insights. And thank you, listeners, for tuning in to another episode of Decentralized Application Development Crashcasts. If you've enjoyed today's content, please visit crashcasts.com to learn more. Don't forget to join our Discord community, support us on Patreon, and subscribe to the podcast. Your engagement helps us create better content for you. Until next time, happy coding.